In this video, we continue to study the thermodynamic stability of mixtures by introducing the concept of colligative properties. Alright, so we have a solvent and a solute, and we're trying to study how the presence of the solute affects the properties of the solvent. Right, so colligative properties are a set of properties that depend only on the concentration of the solute and not its nature. Right, so there's three colligative properties that we're going to study. One of them is a boiling point elevation, then the freezing point depression, and the osmotic pressure. And the important thing about those properties is that the nature of the solute actually does not matter. The only thing that matters is the concentration to see how much the boiling point, the freezing point, or the osmotic pressure change. Right, so let's get started here with the boiling point elevation to a solvent upon addition of a solute. If we take a phase diagram for a pure substance, we have here this pressure versus temperature map, which might look like this for a substance that is not water. Here you have your liquid, here you have your gas, and here you have your solid. All right, what we have learned until now is that there is a transformation to this liquid to gas phase boundary, which is the line of vapor pressures or boiling points. We know that according to Raoult's law, the vapor pressure, which is this line of a solid, changes upon addition of a solute. Right? If you don't have any solute, then the mole fraction of the solvent is 1, and that means that your vapor pressure is exactly the vapor pressure of the liquid when pure, and that will be this line, because this is the phase diagram of a pure substance. But as soon as you start to add some solute, then X sub A becomes increasingly different from 1, lower than 1, and that means that the vapor pressure of the solvent decreases, right? So what you actually have is a line that looks like this, right? So the idea is that now, if you're working at a particular pressure, let's say 1 atmosphere, your boiling point is no longer going to be what you actually had in the pure substance, but it's actually going to be right here. Okay, that is your new boiling point, and this is the boiling point of the substance when it was pure. Right? So clearly there is a boiling point elevation. That solvent now is going to boil at higher temperatures at the same pressure than when it was pure. Okay, and it turns out that there is a very simple relationship between the amount of solute that you're adding to the solvent and the change to the boiling point of the solvent, and that is simply this expression. The change to the boiling point is equal to an ebullioscopic constant, which depends on the solvent and on the molality of the solute in the solution. Okay, so it's a linear relationship between the molality of the solute and the boiling point elevation, which makes these calculations pretty simple. Now, something very similar happens to the freezing point. It turns out that when you add a solute to a solvent, the freezing point actually gets depressed. Okay, so you have a new line of the freezing point in this phase diagram, which is shifted towards the left in this diagram. And what that means is that now that solvent, okay, the same pressure does not freeze at this particular temperature, which is what we call the freezing point, but it actually freezes at a lower temperature, which is your freezing point prime, when you have a little bit of solute dissolved into that solvent. Okay, so the boiling point gets elevated, but the freezing point gets depressed. Okay, so there's an analogous expression here for this freezing point depression, okay, where this is simply going to be equal to the cryoscopic constant. It's a constant that depends on the solvent and will be different from the boiling point constant or ebullioscopic constant, but the shape of the equation is actually the same. There's a direct proportionality between the concentration of the solute and the change to the freezing point of that solvent. Now, something that is very important is that this is a positive number, is a boiling point elevation, right? So the final temperature is larger than the initial temperature, and this will be a negative number, which is that's because the freezing point gets depressed. So your new freezing point is actually a little bit lower than your initial freezing point. Right, so generally what we actually do is you just take the absolute value of this number so that we don't have to change the sign of the right-hand side of the equation. All right, these equations work when the solute that you're adding is something that we call a non-electrolyte. Okay, so when that solute does not dissolve into ions in solution. So for example, ethanol, methanol, any alcohol, when you dissolve it in water, they don't form new particles. They stay as they are. They're just the solute dissolved in water. Sugar would be another example, right? It's a non-electrolyte. You put sugar in water, and the sugar molecules stay intact. They don't dissociate into ions. However, you can also dissolve electrolytes, like for example, sodium chloride. Right? When you put this in water, you generate sodium plus and chloride ions in solution. Right? So notice that for every mole of sodium chloride that you generate, there's actually 2 moles of ions in solution. And again, that wouldn't happen for something like methanol, okay, which is a liquid, and then you put it in water, and now you would have aqueous methanol. All right, for every mole of methanol that you have before solution, you actually have 1 mole of methanol after solution. Clearly, if you have the same molality of sodium chloride and methanol, because you have more particles of solute in the sodium chloride solution, you should actually have a larger boiling point elevation and freezing point depression, and actually that is found to be true. So then what we actually do is we take these expressions for the boiling point elevation and freezing point depression and simply correct them by a factor that we call I, and this is what we call the Van Hoff factor. Okay, so I is the Van Hoff factor, and it's simply a measure for how many particles are formed in solution upon solution of the salt or the alcohol, right? So this is the number of particles in solution divided over the number of particles before solution. Alright, so for example, for sodium chloride, notice that for every particle that we have before solution, there's 2 formed in solution, so I would be equal to 2. And then for methanol, every particle that we have in solution is the same as we have before solution, so I is equal to 1. Right, so notice how sodium chloride will actually give twice as large a boiling point elevation and freezing point depression as methanol would, and that is the difference between electrolytes and non-electrolytes. Alright, so in this video we have seen how adding a solute to a solvent modifies the properties of a solvent, and here we have seen the boiling point elevation and a freezing point depression. Now this is a colligative property because the nature of the substance actually doesn't matter. It only matters how much of the substance you have, right? So for example, for methanol, notice that we will get exactly the same change in freezing point and boiling point if it's methanol or ethanol or glucose, right? The only thing that matters is the concentration. Now we have to make a distinction between electrolytes and non-electrolytes, because electrolytes have the ability to generate more particles in solution than non-electrolytes. But that is simply folded into the expression by using this Van Hoff factor that allows you to quantify exactly how the dissolution of electrolytes is different from that of non-electrolytes.